Humanity is trapped. Alpha Centauri is 25 trillion miles away. Your brain cannot comprehend that number. We will probably never reach it. And when you understand why, you'll realize how truly alone we are in this universe. Today, you will understand why that distance might be the loneliest fact in human existence. And here is a question. If you could instantly master any scientific field, which would you choose? Quantum physics, astronomy, or perhaps something else? Let us know in the comments. I will pin the most creative answer. Now let's begin. When we think about space, we often imagine astronauts floating in the International Space Station, robots exploring Mars, or ambitious plans to return humans to the moon. These achievements represent the pinnacle of human ingenuity and determination. Yet, they're all happening within our cosmic backyard, our own solar system. The moment we shift our gaze beyond to the stars themselves, everything changes. The scale becomes so mind-bending that our everyday understanding of distance completely breaks down. Alpha Centauri isn't just any star system. It's our closest neighbor in the galactic neighborhood, a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and the faint red dwarf, Proxima Centauri. To observers in the southern hemisphere, Alpha Centauri appears as one of the brightest points in the night sky, shining with a brilliance that makes it easy to spot with the naked eye. Alpha Centauri A resembles our own Sun, classified as a G-type star, while Alpha Centauri B is slightly smaller and cooler, a K-type star. Then there's Proxima Centauri, the smallest and dimmest of the three, yet holding the title of the absolute closest star to Earth. These stars aren't just distant specks. They're complete worlds unto themselves, burning with nuclear fusion, radiating light and heat across the void. Recent discoveries using the James Webb Space Telescope have even found evidence suggesting a gas giant planet, roughly the mass of Saturn, orbiting Alpha Centauri A. Meanwhile, Proxima Centauri has at least 2 confirmed planets, including Proxima b, which orbits within the habitable zone where liquid water could theoretically exist on a planet's surface. The possibility that one of our nearest neighbors might host conditions suitable for life adds profound urgency to understanding just how far away these worlds truly are. So, how far is Alpha Centauri? The most commonly cited figure is approximately 4.3 light-years. That sounds manageable until you start unpacking what a light-year actually means. A light-year isn't a measure of time, despite the word year in its name. It's a measure of distance, specifically the distance that light travels in 1 year through the vacuum of space. Light moves at an astonishing speed of about 186,000 miles per second, or roughly 300,000 kilometers per second. That's fast enough to circle Earth more than 7 times in a single second. Now imagine light traveling at that incredible velocity continuously without stopping for an entire year, 365 days. 8,760 hours, over 500,000 minutes. Every single second, light covers 186,000 miles. By the end of 1 year, light will have traversed approximately 5.88 trillion miles, or about 9.46 trillion kilometers. That distance represents 1 light year. If you think about it from another angle, consider that sunlight takes roughly 8 minutes and 20 seconds to reach Earth. That means Earth sits about 8 light minutes from the Sun. Neptune, the outermost planet in our solar system, orbits at a distance of about 4 light hours. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object, has traveled for nearly 50 years and is currently about 24 light hours away from Earth. It has just barely begun to scratch the surface of interstellar space. Alpha Centauri, at 4.3 light-years away, sits roughly 37,000 times farther from us than Neptune. To put it in raw numbers, Alpha Centauri is approximately 25 trillion miles distant, or about 40 trillion kilometers. If you could somehow drive a car to Alpha Centauri at highway speeds of 60 miles per hour without stopping for food, sleep, or fuel, the journey would take you more than 48 million years. That's longer than modern humans have existed on Earth. Let me hit you with another comparison. If you scaled down the entire distance from Earth to Alpha Centauri and represented our Sun as a basketball, Alpha Centauri would be another basketball located roughly 6,000 miles away. That's approximately the distance from New York City to Paris. Now imagine trying to throw something from New York and hitting a basketball sitting in Paris. That gives you some sense of the cosmic gulf we're dealing with. But wait, it gets even more humbling. We've built some of the fastest spacecraft ever conceived by human minds. The Parker Solar Probe, a NASA mission designed to study the Sun's outer atmosphere, currently holds the record as the fastest human-made object ever constructed. On December 24, 2024, during its closest approach to the Sun, Parker Solar Probe reached a blistering speed of 192 kilometers per second, which translates to about 430,000 miles per hour. That's fast enough to travel from New York to Tokyo in less than 1 minute. It's a speed so extreme that the spacecraft experiences forces and temperatures that would vaporize almost any material known to humanity, requiring cutting-edge heat shields and technology to survive. Even at that incredible velocity, if we pointed Parker Solar Probe directly at Alpha Centauri and it maintained that top speed indefinitely, the journey would still take approximately 6,500 years. Think about that for a moment. 6,500 years ago, humans were just beginning to develop writing systems. The pyramids of Egypt hadn't been built yet. Entire civilizations have risen and fallen in shorter time spans. Yet that's how long it would take our fastest spacecraft to reach our nearest stellar neighbor. The reality is even more daunting because spacecraft don't maintain constant speeds. They require fuel for course corrections, they slow down as they move away from gravitational assists, and they face countless technical challenges over decades of operation. Voyager 1, for instance, travels at about 38,000 miles per hour, a respectable speed for deep space missions. If Voyager 1 were headed directly toward Alpha Centauri instead of its current trajectory, it would arrive in roughly 73,000 years. That's nearly 15 times longer than recorded human history. Understanding these distances forces us to confront an uncomfortable truth about our existence. We are incredibly isolated in the universe. Every human who has ever lived, every story ever told, every war fought, every discovery made, has occurred on one small planet, orbiting one average star in one corner of one galaxy. The nearest potentially habitable world beyond our solar system could be sitting right next door in cosmic terms at Proxima Centauri b, yet it remains utterly unreachable with current technology. Scientists and engineers have known about this challenge for decades, and they haven't been sitting idle. Creative minds have proposed numerous solutions to the problem of interstellar travel, each with its own set of incredible promises and formidable obstacles. One of the most ambitious recent efforts is called Breakthrough Starshot, a project announced in 2016 with backing from some of the world's wealthiest individuals and brightest minds in physics and engineering. Breakthrough Starshot envisions a radically different approach to space travel. Instead of building massive spacecraft loaded with fuel, the project proposes sending thousands of tiny probes, each no bigger than a microchip, accelerated to approximately 20% the speed of light using powerful ground-based lasers. These miniature spacecraft, called sprites, would weigh only a few grams and be equipped with cameras, sensors, and communication equipment. A massive array of lasers on Earth would focus their combined energy onto ultra-lightweight light sails attached to each sprite, pushing them to velocities we've never achieved before. At 20% light speed, these probes could theoretically reach Alpha Centauri in about 20 years after launch. Add another 4 years for the signals and images to travel back to Earth at the speed of light, and you're looking at roughly a 24-year mission from launch to data return. Suddenly, interstellar exploration shifts from a multi-generational endeavor into something that could happen within a single human lifetime. That's genuinely revolutionary. And if you are enjoying learning about these mind-blowing facts about our universe, don't forget to subscribe and hit that thumbs up button. Your support helps this channel grow and allows me to keep bringing you fascinating cosmic content. Recent updates from early 2026 confirm that Breakthrough Starshot's Phase 1 has successfully met its stated objectives. The team identified potential showstoppers in beam-driven interstellar propulsion and determined that credible solutions exist for each major challenge. Scientists have published numerous papers on topics ranging from laser array designs to metamaterials for light sails, from navigation at relativistic speeds to data transmission across light-year distances. While the project was placed on hold in 2024 to restructure for its next phase and seek broader support, it has not been cancelled, contrary to some media reports. The engineering challenges remain staggering. Building a laser array powerful enough to accelerate these probes requires an energy output comparable to that of a large power plant, focused into a beam with extraordinary precision. The light sails must be incredibly thin yet strong enough to withstand the intense laser radiation without tearing or vaporizing. The sprites themselves must survive acceleration forces, cosmic radiation, collisions with interstellar dust, and extreme temperatures, all while weighing only a few grams. Then there's the matter of communicating with a probe traveling at 60,000 kilometers per second across trillions of miles of space. Yet, despite these obstacles, the fact that serious scientists and engineers consider Breakthrough Starshot feasible represents a profound shift in our thinking about interstellar travel. We're moving from impossible to extraordinarily difficult, but potentially achievable. Beyond the technological marvels of projects like Breakthrough Starshot lies an even deeper question. What would it actually feel like to attempt this journey? Not as a tiny probe, but as a human being. This is where the true terror of interstellar distance reveals itself, because we're not just talking about numbers on a page anymore, we're talking about the lived experience of confronting cosmic emptiness. Imagine for a moment that we somehow developed a spacecraft capable of sustaining human life for the duration of an interstellar voyage. Let's be wildly optimistic and assume we've created a vessel that can accelerate to 1% of light speed, 10 times faster than any current spacecraft, but still a fraction of what Breakthrough Starshot aims for with its tiny probes. At that velocity, the journey to Alpha Centauri would take approximately 430 years. 430 years. Think about what that means. You would board the spacecraft as a young adult, along with hundreds or perhaps thousands of other carefully selected individuals. You would live your entire life aboard this vessel, traveling through the absolute void of space. You would have children aboard the ship, and those children would have children, and those grandchildren would have children of their own. Roughly 15 to 20 generations would be born, live, and die aboard that spacecraft before anyone reached the destination. The people who finally arrived at Alpha Centauri would be so far removed from the original crew that Earth itself would seem like ancient mythology to them. This concept, known as a generation ship, has fascinated science fiction writers for decades, but the psychological and social realities are genuinely terrifying. How do you maintain a stable society for 4 centuries in an enclosed environment? How do you preserve knowledge, culture, and the original mission's purpose across 20 generations? What happens if people born on the ship decide they don't want to continue the journey? What if the destination turns out to be uninhabitable and the entire voyage was for nothing? The isolation would be absolute in ways difficult for us to comprehend. Once you travel far enough from Earth, looking back toward our solar system, the Sun becomes just another star in the sky, no brighter or more significant than any other. There would be no rescue missions if something went wrong, no resupply ships, no communication that doesn't involve years of delay. You would be truly, utterly alone in the cosmos, surrounded by darkness so complete and vast that it defies human imagination. Speaking of darkness and cold, if you found this exploration of cosmic distances fascinating, you might enjoy diving deeper into another aspect of space's hostility. I've created a detailed video called The Terrifying Truth About How Cold Space Really Is, which explores the extreme temperatures and conditions that exist in the void between stars. The environment around Alpha Centauri, despite being near a star system, would subject any travelers to temperature extremes and radiation that make Earth's harshest environments look comfortable. Check out that video after this one. The link is in the description and on the card above. Now let's consider another approach that scientists have theorized: cryogenic sleep or suspended animation. This staple of science fiction proposes freezing human travelers or drastically slowing their metabolism so they could sleep through the journey, aging minimally while decades or centuries pass. If such technology existed and worked perfectly, it would solve many of the generation ship problems. You could potentially board a spacecraft, enter suspended animation, and wake up decades later in orbit around a new star system, having aged only days or weeks. The problem is that we're nowhere close to making this reality. Current cryogenic techniques can preserve cells, tissues, and even some small organisms for extended periods. But bringing a complete human being with a functioning brain back from suspended animation remains firmly in the realm of science fiction. The challenges are immense. Ice crystals forming during the freezing process destroy cellular structures. Brain tissue is particularly vulnerable to damage. Even if we solved the freezing problem, we'd need automated systems reliable enough to maintain a spacecraft for centuries without human intervention and then safely revive the crew at precisely the right moment. Some researchers have explored the concept of embryo space colonization, which sounds like something from a dystopian novel but represents a theoretically more feasible approach. Instead of transporting living adults, a spacecraft would carry frozen embryos, genetic material, and advanced robotic systems capable of nurturing and raising children upon arrival at the destination. The robots would serve as caretakers and educators, teaching the first generation everything they need to know about their mission and their distant Earth origins. This approach solves many technical problems. Embryos require far less life support than conscious adults. The spacecraft can be smaller and lighter without needing generations of living space, but the ethical questions are staggering. Is it morally acceptable to create human beings who will never know their biological parents, never experience Earth, and exist solely to colonize another world? Who makes decisions about their upbringing, their education, their values? The concept pushes the boundaries of what we consider acceptable treatment of human life. Let's shift perspective for a moment and consider what we could actually accomplish if we did reach Alpha Centauri. What would we find there? The system's most intriguing world, Proxima Centauri b, orbits the smallest and coolest of the three stars at a distance of roughly 7 million kilometers. That places it well within Proxima Centauri's habitable zone, the region where temperatures could theoretically allow liquid water to exist on a planet's surface. Proxima b has a mass roughly similar to Earth's, perhaps 10 to 20% more massive, which suggests it could be a rocky world rather than a gas giant. These facts alone have generated tremendous excitement in the scientific community. A potentially rocky planet in the habitable zone of the closest star system to Earth represents one of the most compelling targets for the search for extraterrestrial life that we could possibly hope for. However, and this is a crucial point, being in the habitable zone doesn't guarantee habitability. Proxima Centauri is a red dwarf star, a class of stars known for violent stellar activity. These stars regularly unleash powerful flares, bursts of radiation far more intense than anything our Sun produces. A planet orbiting that close to such a temperamental star would be bathed in harmful radiation during these flare events. Over billions of years, this radiation could strip away any atmosphere the planet might have had, leaving behind a barren, airless rock. Furthermore, Proxima b is likely tidally locked to its star, meaning one side of the planet perpetually faces Proxima Centauri while the other side remains in eternal darkness. This happens because the planet orbits so close to its star that gravitational forces have synchronized its rotation with its orbit, the same way the Moon is tidally locked to Earth, so we only ever see one face of it. On a tidally locked planet, you'd have a day side that's constantly scorched by stellar radiation and a night side frozen in permanent darkness. The only potentially habitable region might be a narrow twilight zone between the two extremes, assuming the planet retained an atmosphere capable of redistributing heat. Recent studies examining Proxima b's potential habitability have painted a complex picture. Scientists have used computer models to simulate the planet's formation, its orbital evolution, and its interaction with Proxima Centauri's radiation over billions of years. Some models suggest that Proxima b could have retained water and a protective atmosphere if it formed farther from the star and migrated inward later, or if it possessed a strong magnetic field to deflect stellar radiation. Other models indicate the planet likely lost most of its volatiles early in its history and now resembles a larger, more massive version of Mars, cold, dry, and essentially dead. We simply don't know yet which scenario is correct. That uncertainty highlights both the promise and the frustration of exoplanet science. We can detect these worlds, measure their masses and orbits, and make educated guesses about their compositions, but we can't yet observe them in enough detail to definitively answer whether they host life or even have breathable atmospheres. That's what makes the distance to Alpha Centauri so agonizing. If Proxima b were in our solar system, we could send robotic missions there within years or decades using current technology. We could orbit the planet, land on its surface, analyze its rocks and atmosphere, and determine once and for all whether it represents a second home for life in the universe. But it's not in our solar system. It's 4.2 light-years away, separated from us by a gulf so vast that our fastest spacecraft would take thousands of years to cross it. The same James Webb Space Telescope that recently found evidence of a possible gas giant around Alpha Centauri A demonstrates how much our observational capabilities have advanced. Webb represents the cutting edge of astronomical technology, able to peer deeper into space and observe fainter objects than any previous telescope. Yet even Webb cannot directly image the surface of Proxima b or analyze its atmosphere in detail. The planet is simply too small, too dim, and too close to its bright star for current instruments to resolve with the necessary precision. Future telescopes now in the planning stages might change that situation. Concepts for extremely large ground-based observatories and advanced space telescopes specifically designed to image exoplanets could potentially observe atmospheric signatures from worlds like Proxima b within the next few decades. If we detected oxygen, methane, or other biosignature gases in Proxima b's atmosphere, assuming it has one, that discovery would rank among the most profound in human history. It would confirm that life exists beyond Earth and that our nearest stellar neighbor might harbor a living world. But here's the cruel irony. Even if we definitively discovered life on Proxima b tomorrow, we still couldn't go there. The distance remains insurmountable with current technology. We would be in the frustrating position of knowing that life exists a mere 4 light-years away, tantalizingly close in cosmic terms, yet completely unreachable. We could observe from afar, perhaps even communicate if the life were intelligent, though conversations involving 8+ years between question and answer would test anyone's patience. But we couldn't touch it, sample it, study it up close, or walk on its surface. This profound disconnect between knowing and reaching represents one of the most maddening aspects of modern astronomy. Our telescopes have become cosmic time machines, revealing galaxies billions of light-years distant, showing us the universe as it existed when it was young and chaotic. We can observe the birth of stars in distant nebulae, watch black holes devour matter, and trace the evolution of cosmic structures across unimaginable spans of time and space. Yet we remain confined to one tiny blue marble, unable to physically explore even the nearest points of light in our night sky. The history of exploration on Earth offers both inspiration and cautionary tales when we think about interstellar travel. For most of human existence, our ancestors were limited to the land they could reach on foot. Crossing an ocean was unthinkable, impossible, the realm of myth and legend. Then we developed boats, simple vessels at first, capable of hugging coastlines and venturing into calm waters. Over centuries, those boats became ships, and those ships became capable of crossing oceans, connecting continents, and ultimately circumnavigating the entire globe. The parallels to space exploration seem obvious. We started with simple rockets capable of barely reaching the edge of space. Then we built vehicles that could orbit Earth, travel to the Moon, and send robotic probes throughout the solar system. Surely, the optimistic thinking goes, we'll continue that progression until interstellar travel becomes as routine as intercontinental flights are today. But there's a critical difference. When ancient Polynesians sailed across the Pacific Ocean, discovering and settling remote islands separated by thousands of miles of open water, they were undertaking extraordinarily dangerous voyages that pushed human endurance to its limits. Many expeditions undoubtedly failed, lost to storms, starvation, or simple navigational errors. Yet those distances, while vast by human standards, were still fundamentally conquerable. A journey of several thousand miles, even in a primitive outrigger canoe, could be completed in weeks or months. The travelers could bring enough food and water, they could navigate by stars and ocean swells. When they reached land, that land offered everything they needed to survive: fresh water, food sources, materials for shelter. Interstellar space offers none of these advantages. The distance isn't merely vast, it's vast on a scale that dwarfs anything humans encountered on Earth. There are no islands to rest at along the way, no chances to resupply, no possibility of turning back if conditions become unfavorable. The journey would take not weeks or months, but centuries or millennia with foreseeable technology. And the destination, even if it's a potentially habitable planet like Proxima b, might turn out to be hostile to human life in ways we can't anticipate until we arrive. Some scientists have proposed alternative propulsion systems that could theoretically enable faster interstellar travel. Nuclear pulse propulsion, first seriously studied in the 1950s and 60s under Project Orion, involves detonating nuclear bombs behind a spacecraft and riding the shock waves to achieve tremendous velocities. The concept sounds insane, and it faces obvious technical and political challenges, particularly regarding the detonation of nuclear weapons in space. However, calculations suggest that a nuclear pulse spacecraft could potentially reach several percent of light speed, reducing the journey to Alpha Centauri to perhaps 100 years or less. Antimatter propulsion represents another theoretical possibility. When matter and antimatter come into contact, they annihilate each other in a burst of pure energy, according to Einstein's famous equation E equals mc squared. The energy released is far greater than any chemical or nuclear reaction. A spacecraft powered by matter-antimatter annihilation could theoretically achieve significant fractions of light speed, maybe 10 to 20% or even higher, cutting travel times to decades rather than centuries. The catch, and it's a significant one, is that antimatter doesn't exist naturally in any useful quantities in our corner of the universe. We can create tiny amounts in particle accelerators, literally a few atoms at a time, at enormous expense. Producing and storing the kilograms or tons of antimatter needed for an interstellar mission remains far beyond our current capabilities. Even if we solved the production problem, containing antimatter without letting it touch normal matter and annihilate prematurely presents engineering challenges that make rocket science look simple by comparison. Fusion propulsion, harnessing the same nuclear reactions that power the Sun, offers a more plausible near-term option. Unlike antimatter, the fuel for fusion reactions, isotopes of hydrogen like deuterium and tritium, exists in relatively abundant quantities. A fusion rocket could theoretically accelerate continuously for years, gradually building up to velocities measured in significant percentages of light speed. Multiple research groups and space agencies have studied fusion propulsion concepts, and some limited experimental work continues, though we're still decades away from a functional fusion rocket. Even with fusion propulsion reaching perhaps 5 to 10% of light speed, we're still looking at journey times to Alpha Centauri of 40 to 80 years. That's less daunting than thousands of years, but still represents an enormous commitment. Everyone who departed on such a mission would likely die before arrival, unless we somehow developed life extension technologies or that elusive, suspended animation capability. There's also the small matter of slowing down once you get there. When we send probes to Mars or Jupiter, they can use aerobraking, friction with a planet's atmosphere, to shed velocity or gravitational assists from other planets to adjust their trajectories. In interstellar space, there are no convenient planets to use for braking. If you accelerate to 10% of light speed on the way to Alpha Centauri, you need to figure out how to decelerate when you arrive, or you'll simply blow past the star system too quickly to accomplish anything useful. One solution is to carry enough fuel to decelerate, but that means carrying even more fuel at the start of the journey to accelerate all that deceleration fuel, which quickly spirals into impossible mass requirements. The rocket equation, that fundamental limitation of conventional propulsion, rears its head again. Another option is to use magnetic sails or light sails for braking, deploying massive structures that interact with the destination star's radiation or stellar wind to gradually slow down. This adds complexity, mass, and additional failure points to an already incredibly complex mission. Let's talk about the radiation environment in interstellar space, because this represents yet another layer of danger that science fiction often glosses over. Space isn't empty, despite what the name suggests. It's filled with cosmic rays, high-energy particles traveling at nearly the speed of light, originating from supernovae, black holes, and other violent cosmic events. Here on Earth, we're protected from cosmic rays by our planet's magnetic field and atmosphere, which deflect or absorb most of this radiation before it can reach the surface. A spacecraft traveling through interstellar space has no such protection. Crew members or sensitive electronics would be constantly bombarded by cosmic rays. Over months and years, this exposure accumulates, increasing cancer risks, damaging DNA, degrading electronics, and potentially causing neurological problems. Shielding against cosmic rays is extremely difficult because the particles are so energetic they can penetrate substantial amounts of material. Water, hydrogen-rich plastics, or meters-thick layers of metal provide some protection, but all that shielding adds mass, which makes the spacecraft harder to accelerate and slows down the journey. At higher velocities, even interstellar dust and gas become hazards. Space between stars isn't a perfect vacuum. It contains roughly 1 atom per cubic centimeter on average, mostly hydrogen. That sounds incredibly sparse, and it is, far emptier than the best vacuum we can create on Earth. But when you're traveling at 10% of light speed, collisions with even individual atoms release significant energy. A grain of dust the size of a sand particle hitting a spacecraft at that velocity would impact with the energy of a hand grenade. Larger debris, pebbles, or anything more substantial would be utterly catastrophic. This means an interstellar spacecraft needs not just radiation shielding, but also impact protection. Some designs propose using magnetic fields to deflect charged particles, essentially creating an artificial magnetosphere around the ship. Others suggest a sacrificial shield, a thick layer of material at the front of the spacecraft designed to absorb impacts and slowly erode away during the journey. These protective measures add yet more mass and complexity to an already monumental engineering challenge. Navigation at interstellar distances presents its own unique problems. On Earth, we navigate using landmarks, compasses that respond to our planet's magnetic field, or GPS satellites. In space near Earth, we can use star positions and radio signals from ground stations, but traveling between stars, you're working with positional uncertainties that accumulate over time. A tiny error in your trajectory at the beginning of the journey, even a fraction of a degree, compounds over trillions of miles until you could miss your target star system entirely. Modern spacecraft use incredibly precise navigation techniques, but maintaining that precision over interstellar distances requires constant course corrections. That means using fuel for those corrections, which again brings us back to the mass problem. It also means having reliable sensors and computer systems that continue functioning for the entire journey duration. Every component must work perfectly for decades, centuries, or millennia, depending on the mission profile. There are no repair shops in interstellar space, no way to order replacement parts, no technicians who can come fix a broken sensor. The Voyager spacecraft, launched in 1977, provide our only real-world data on spacecraft longevity in deep space. Both Voyager 1 and Voyager 2 continue to function after nearly 50 years, sending back data from beyond the edge of our solar system. This represents an astonishing achievement in engineering and design. The spacecraft were built with redundant systems, radiation-hardened electronics, and nuclear power sources that have far outlasted their original design lifespans. Yet even the Voyagers are failing gradually. Their radioactive power sources decay over time, providing less electricity with each passing year. NASA engineers have had to systematically shut down instruments and heaters to conserve power. Within the next decade or so, the Voyagers will go silent, their nuclear batteries finally depleted, leaving them to drift through space as dead, silent monuments to human ambition. If the Voyagers were headed toward Alpha Centauri, they wouldn't arrive for another 73,000 years, and they'd be long dead by the time they got there, unable to observe anything or send back any information. This illustrates the central dilemma of interstellar exploration with current technology. We can build machines that survive for decades in space, which is remarkable, but we need machines that survive for centuries or millennia, which is a completely different challenge. The psychological dimensions of interstellar travel deserve serious consideration because they're just as challenging as the physics and engineering problems. Human beings evolved to live on the surface of a planet with open skies, changing seasons, and complex ecosystems. We're social creatures who need interaction, novelty, and purpose to maintain mental health. Confining people to a spacecraft for their entire lives, even a large one, creates conditions utterly unlike anything in our evolutionary history. Studies of isolated and confined environments here on Earth provide some insights, though the parallels are imperfect. Antarctic research stations, submarines, space stations, and various isolation experiments have shown that people can adapt to confined spaces for extended periods, but not without psychological costs. Conflicts arise over trivial matters. People develop depression, anxiety, and interpersonal problems. The knowledge that you can leave, that the isolation is temporary, helps people endure these conditions. Remove that knowledge, make the confinement permanent and multi-generational, and you're entering completely uncharted psychological territory. Imagine being born on a generation ship, growing up, knowing that you'll never set foot on a planet, never experience rain or wind, never see a horizon that isn't a metal bulkhead. Your entire world is corridors and compartments, recycled air and artificial light. You've been told stories about Earth, seen videos and images, but it's all abstract, no more real to you than ancient mythology. Meanwhile, you're expected to maintain complex systems, raise children, and preserve a mission that won't be completed for 10 more generations. What motivates you? What gives your life meaning and purpose? Some researchers studying generation ships have proposed creating artificial environments that mimic Earth as closely as possible. Rotating sections of the spacecraft could provide artificial gravity through centrifugal force, preventing the bone loss and muscle atrophy that plague astronauts in zero gravity. Hydroponic gardens and agricultural sections could grow food, while also providing green spaces that fulfill psychological needs. Advanced lighting systems could simulate day-night cycles and seasonal changes. Virtual reality technology might allow crew members to experience simulated outdoor environments, oceans, forests, mountains, anything to break the monotony of metal walls. But these are band-aids on a fundamental problem. No amount of clever engineering can change the basic reality that you're trapped in a box, hurtling through an endless void, surrounded by a universe that's actively trying to kill you with radiation, vacuum, extreme temperatures, and the sheer, crushing emptiness of space. Generation after generation would need to find reasons to continue to maintain hope, to believe that the destination justifies the sacrifice of every life spent traveling. Religious and philosophical frameworks might help. Many human cultures have sustained themselves through hardship by focusing on purposes larger than individual lives. The passengers might view themselves as carrying the torch of human civilization to a new world, becoming ancestors to billions of future descendants who will live under alien skies. That's a powerful narrative, one that could potentially sustain people through the grinding reality of shipboard life. But it also requires a level of faith and commitment that's difficult to maintain across multiple generations who never knew Earth and never will see Alpha Centauri. There's also the distinct possibility of social fragmentation and rebellion. What if a generation decides they don't want to continue toward Alpha Centauri? What if they want to turn around and try to return to Earth, or alter course toward a different star system, or simply stop accelerating and establish a permanent nomadic existence in interstellar space? The mission planners on Earth, long dead by this point, can't enforce compliance. Authority on the ship would rest with whoever the crew recognizes as legitimate leaders, and those leaders might have very different priorities than the original mission. Science fiction has explored these scenarios extensively. Stories of generation ships that forgot their purpose, descended into barbarism, or split into warring factions aren't just dramatic narratives. They represent genuine concerns about maintaining social cohesion over timescales longer than any human civilization has ever endured. The longest-lasting continuous civilizations on Earth, ancient Egypt or China, persisted for a few thousand years with tremendous changes in government, culture, and technology. A generation ship represents a closed system where dramatic social change could threaten the entire mission's survival. Let's consider the economic aspects of interstellar travel because they're equally daunting. Building a spacecraft capable of carrying humans to another star system would be the most expensive project in human history by orders of magnitude. Estimates for missions like Breakthrough Starshot run into billions of dollars just to develop and launch tiny probes. A crewed mission would cost trillions, perhaps tens of trillions of dollars, spread over decades of construction and preparation. Who pays for such a venture? Individual nations struggle to fund space programs that operate within our own solar system. The International Space Station, humanity's greatest achievement in space cooperation, cost roughly $150 billion over its construction and operational lifetime, funded by multiple nations pooling resources. An interstellar generation ship would dwarf those costs while offering no economic return within the lifetimes of anyone who funded it. Private companies and wealthy individuals have shown interest in space exploration recently. Companies like SpaceX, Blue Origin, and others are developing technologies that reduce launch costs and enable more ambitious missions. Breakthrough Starshot itself receives funding from private philanthropists. But there's a vast difference between funding rocket development or even Mars colonization, where results and potential returns come within decades, and funding an interstellar mission where everyone involved in the planning and construction will be dead centuries before it succeeds or fails. Perhaps the only realistic scenario for funding interstellar travel involves a fundamental shift in human civilization. If we become a spacefaring species that routinely exploits resources throughout our solar system, establishing permanent settlements on the Moon, Mars, asteroids, and moons of the outer planets, then the resource base for attempting interstellar missions becomes more plausible. A civilization with millions or billions of people living throughout the solar system, mining asteroids, harvesting energy from the sun on industrial scales, might view an interstellar mission as an achievable goal rather than an impossible dream. But we're nowhere near that level of development. Current space activity remains confined to low Earth orbit, with occasional robotic missions venturing further. The total number of humans in space right now, as I record this, is typically fewer than 10, all aboard the International Space Station. We haven't returned to the Moon since 1972, over 50 years ago. Mars remains unvisited by humans. The gap between our current capabilities and what would be required for interstellar travel is so enormous that it's difficult to visualize. Some people find this situation depressing. We've identified potentially habitable worlds orbiting nearby stars. We know they exist, we've seen them, yet we can't reach them. It's like being trapped on an island, seeing other lands on the horizon, but having no way to cross the water. That frustration, that sense of being imprisoned by the laws of physics, drives some of the more speculative proposals for interstellar travel. Concepts like warp drives, wormholes, and other faster-than-light travel methods appear regularly in science fiction and occasionally in serious physics papers. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical method of warping space-time itself to create a bubble that could move faster than light without actually violating relativity. The spacecraft inside the bubble wouldn't be moving through space faster than light. Space itself would be contracting in front of the ship and expanding behind it, carrying the vessel along. It's an elegant idea that respects the mathematical structure of Einstein's general relativity. The problem is that it requires exotic matter with negative energy density, something we've never observed and don't know how to create. The energy requirements, even in optimistic calculations, range from the mass energy of entire planets to the total energy output of the Sun for extended periods. Some physicists argue the concept is fundamentally impossible, that quantum effects or other physical principles we don't fully understand would prevent such space-time manipulation. Wormholes, hypothetical tunnels through space-time connecting distant regions of the universe, face similar problems. They appear as valid solutions to Einstein's equations, but stabilizing a wormhole large enough for a spacecraft to traverse would again require exotic matter and energies far beyond anything we can produce. Even if we could create and stabilize a wormhole, we'd need to position one end near Alpha Centauri somehow, which brings us right back to the original problem of getting there in the first place. These concepts aren't completely useless. They push the boundaries of theoretical physics, helping us understand the fundamental nature of space-time, energy, and matter. They inspire new generations of scientists and engineers to think creatively about seemingly impossible challenges. But for practical purposes, for actual mission planning, we need to work with technologies and physics we understand and can implement with foreseeable resources. The more we confront the reality of interstellar distances, the more we're forced to reconsider what exploration actually means in a cosmic context. For most of human history, exploration meant humans physically traveling to new places, planting flags, establishing settlements, and bringing back stories and treasures. But perhaps that model doesn't scale to interstellar distances. Perhaps we need to reimagine exploration as something fundamentally different when the destinations are light years away. Robotic exploration represents our most realistic, near-term option for studying other star systems. We've already proven extraordinarily successful at exploring our solar system with robotic probes. Rovers on Mars have operated for years beyond their design lifetimes, climbing mountains, drilling into rocks, analyzing soil chemistry, and searching for signs of ancient life. Orbiters around Jupiter, Saturn, and other worlds have revealed alien landscapes of breathtaking beauty and scientific importance. The New Horizons probe gave us our first close-up views of Pluto in 2015, showing a geologically active world far more complex than anyone expected. These missions succeed because robots don't need life support, don't get bored or depressed, don't require return trips, and can be designed to withstand conditions that would kill humans instantly. A robotic probe to Alpha Centauri could be much smaller and lighter than a crewed spacecraft, making it easier to accelerate to high speeds. It wouldn't need decades of food, water, and air. It could survive radiation levels that would be lethal to humans. If systems failed, nobody dies, we just lose data. Breakthrough Starshot's approach of sending thousands of tiny probes rather than one large spacecraft introduces redundancy into the mission design. If 90% of the probes fail during the journey, which seems likely given the harsh environment and the distances involved, the remaining 10% could still return valuable data. Each probe would carry cameras and sensors tailored to specific scientific objectives. Some might focus on imaging the Alpha Centauri planets, others on measuring magnetic fields, analyzing stellar wind composition, or detecting radio signals that might indicate technological civilizations. The diversity of data from multiple probes arriving at slightly different times and trajectories would provide a much richer scientific return than any single spacecraft could achieve. It's a fundamentally different philosophy from traditional space missions, where everything depends on one vehicle functioning perfectly. Instead, you accept high failure rates, but compensate with large numbers and low individual costs. Communication with these probes presents fascinating challenges. At 20% light speed, a breakthrough Starshot probe would reach Alpha Centauri in roughly 20 years. But the data it collected, transmitted back to Earth at light speed, would take another 4.3 years to arrive. So you're looking at approximately 24 years from launch until scientists on Earth receive the first images and measurements from another star system. That delay fundamentally changes the nature of exploration. There's no possibility of real-time control or interaction. You can't see something interesting and decide to investigate further. Every decision about what to observe, when to activate instruments, and how to allocate limited power and bandwidth must be programmed before launch, or rely on autonomous artificial intelligence systems that can make decisions without human input. The probes would need to be smart enough to identify interesting targets, prioritize observations, and handle unexpected situations. If a probe detected signs of a planet's atmosphere or unusual chemical signatures, it should be capable of adjusting its observation strategy to gather more data on that specific discovery. This requires levels of artificial intelligence and autonomous decision-making that push the boundaries of current technology, though advances in machine learning and AI over recent years suggest we're moving in the right direction. Data transmission across 4 light-years with a transmitter massing only a few grams presents another enormous challenge. Radio signals weaken with distance according to the inverse square law. Double the distance and the signal becomes 4 times weaker. At 4 light-years, signals from a tiny spacecraft would be incredibly faint by the time they reached Earth. Detecting and decoding those signals would require enormous receiving antennas and sophisticated signal processing techniques. Breakthrough Starshot proposes using the same laser array that accelerated the probes as a receiver, turning it into a massive phased array capable of detecting extremely weak signals. The sprites would transmit using lasers rather than radio waves, focusing their limited power into tight beams aimed at Earth. Even so, the data rates would be painfully slow by modern standards, perhaps only a few bits per second. Transmitting even a single high-resolution image might take hours or days. This means mission planners must carefully prioritize what data to send back. You can't transmit everything the probe observes. Instead, the probe must identify the most scientifically valuable observations, compress the data efficiently, and transmit those priority items first. Lower priority data might take months or years to transmit completely. Some data might never be transmitted at all if something more interesting is discovered, or if the probe's power runs out. Despite all these limitations and challenges, robotic missions to Alpha Centauri remain infinitely more feasible than crewed missions with anything resembling current or near-future technology. This has led some scientists and philosophers to argue that we should abandon the dream of humans traveling to other stars, at least for the foreseeable future, and focus instead on robotic exploration and remote sensing. Advanced telescopes, both ground-based and in space, continue improving at remarkable rates. The James Webb Space Telescope represents a quantum leap in our ability to observe distant worlds. Future observatories now being planned, like the Habitable Worlds Observatory or extremely large ground-based telescopes with apertures of 30 meters or more, will be able to directly image some exoplanets and analyze their atmospheric compositions in detail. These observations won't tell us everything. We can't experience what it's like to stand on the surface of Proxima b or taste the chemistry of an alien ocean with remote sensing alone. But we can answer fundamental questions about habitability, the presence of water, atmospheric composition, surface temperature, and even potential biosignatures like oxygen or methane that might indicate life. For many scientific purposes, that information is enough to revolutionize our understanding of life's place in the universe. Imagine detecting oxygen and methane simultaneously in Proxima b's atmosphere, assuming it has an atmosphere we can observe. On Earth, this combination of gases represents a strong biosignature because methane and oxygen react with each other chemically. The fact that both exist in our atmosphere simultaneously requires constant replenishment, and on Earth, life provides that replenishment. Finding the same combination on another world wouldn't prove life exists there. Other geological processes might produce similar results, but it would be extraordinarily compelling evidence worth investigating further. If we did detect such biosignatures, the frustration of not being able to visit would be immense. We'd know that life exists just 4 light-years away, that we share the universe with other living things, but we couldn't study them directly, couldn't answer questions about their biochemistry, their evolution, their relationship to Earth life. We'd be tantalizingly close in cosmic terms, yet impossibly far in practical terms. This situation might actually describe our future for centuries or even millennia. We might discover life on dozens or hundreds of nearby worlds using advanced telescopes, cataloging a cosmic zoo of alien biospheres, atmospheric chemistries, and potentially even technological civilizations, all while remaining confined to our own solar system, able to observe but never to visit. Some people find this prospect acceptable or even preferable. Observation without contact avoids the ethical complications of disturbing alien ecosystems or potentially contaminating them with Earth life. It prevents conflicts over resources or territory. It allows alien life to evolve and develop without interference from humans. We become cosmic naturalists, studying the universe through our telescopes like biologists observing wildlife through binoculars, present but not intrusive. Others find this scenario deeply unsatisfying. Humans are explorers by nature. We've climbed every mountain, crossed every ocean, visited both poles, and set foot on the moon. The idea of knowing that habitable worlds exist nearby, but accepting that we can never visit them, that we must remain forever confined to our birth system, contradicts something fundamental in our psychology. We want to go there, to see with our own eyes, to walk on alien soil, to know what it feels like to stand beneath the light of another sun. This tension between what we want to do and what we can actually achieve with known physics defines the current era of space exploration. We're caught between the incredible expansion of our knowledge about the universe, discovering thousands of exoplanets and potentially habitable worlds, and the harsh reality that our technology remains primitively inadequate for crossing the vast gulfs between stars. The question then becomes, do we accept these limitations as permanent features of existence, or do we treat them as temporary obstacles to be overcome with sufficient time, ingenuity, and resources? History suggests that technological progress often exceeds our expectations. Things that seemed impossible become routine. Flying machines, nuclear energy, computers, genetic engineering, all of these were once dismissed as fantasy before becoming mundane reality. But history also teaches us that some barriers are more fundamental than others. We haven't repealed the laws of thermodynamics or figured out perpetual motion machines despite centuries of trying. We haven't exceeded the speed of light despite numerous claims and experiments. Some limitations appear to be built into the structure of reality itself, not merely engineering challenges waiting for clever solutions. The speed of light might be one of those fundamental limits. Einstein's special relativity, confirmed by over a century of experiments and observations, indicates that nothing with mass can reach or exceed light speed. As objects approach light speed, they require exponentially more energy to continue accelerating. Reaching actual light speed would require infinite energy, which is obviously impossible. This isn't an engineering problem, it's a fundamental property of space-time itself. Even traveling at velocities approaching light speed introduces relativistic effects that fundamentally alter the experience of interstellar travel. Time dilation, one of the strangest predictions of special relativity, means that time passes more slowly for travelers moving at high speeds relative to stationary observers. If you could somehow accelerate a spacecraft to 90% of light speed, time aboard the ship would pass at roughly 43% the rate of time on Earth. A journey that takes 5 years from the traveler's perspective would consume nearly 12 years of Earth time. This effect becomes more pronounced as you approach light speed. At 99% of light speed, time dilation increases dramatically. A journey to Alpha Centauri might take only about 8 months from the traveler's perspective, while more than 4 years would pass on Earth. At 99.9% of light speed, the journey time for travelers shrinks to just over 2 months, while Earth-based observers still measure 4.3 years. This creates a bizarre asymmetry. Travelers could potentially visit nearby stars within their own lifetimes, experiencing months or years of journey time, while decades or centuries pass on Earth. They would return to find everyone they knew aged or dead, society transformed beyond recognition, technology advanced to unimaginable levels. They'd be time travelers moving into Earth's future, exiled from their own era by the journey itself. Science fiction explores these concepts extensively, but the practical implications are deeply unsettling. Would you volunteer for a mission knowing you'd return to find your children elderly or dead? Knowing that the civilization you left might no longer exist, replaced by something alien and unfamiliar? The psychological burden of time dilation might be as challenging as the physical journey itself. There's also the matter of achieving such velocities in the first place. Accelerating even a small spacecraft to 99% of light speed requires energies that dwarf anything our current civilization can produce. Remember, relativistic mass increases as velocity increases. The faster you go, the more massive you effectively become, requiring even more energy to accelerate further. The energy requirements spiral into astronomical figures, literally measured in significant fractions of stellar output. Some theoretical physicists have proposed using the resources of entire star systems to build structures capable of channeling stellar energy for interstellar propulsion. A Dyson sphere, or Dyson swarm, hypothetical megastructures that surround a star to capture its energy output, could potentially provide enough power for relativistic interstellar travel. But building such structures requires engineering capabilities far beyond anything we currently possess. We're talking about projects that would take centuries to complete and require resources measured in planetary masses. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy usage. A Type 1 civilization can harness all the energy available on its home planet. Type 2 controls the energy output of its entire star. Type commands the energy of its entire galaxy. Humanity currently ranks somewhere around 0.7 on this scale, not even Type 1 yet. We use a fraction of the energy that strikes Earth from the Sun, let alone the Sun's total output. Relativistic interstellar travel probably requires Type 2 capabilities, or at least significant progress toward that level. We'd need to be able to manipulate stellar-scale energies, construct megastructures in space, and coordinate projects spanning centuries or millennia. That's so far beyond our current civilization that it's difficult to seriously plan for. We can describe it mathematically, write papers about it, but actually building it remains firmly in the realm of far future speculation. This brings us back to the central terrifying truth about the distance to Alpha Centauri. It's not just that the star system is far away. It's that the distance represents a fundamental barrier separating us from the rest of the universe, a barrier that might take centuries or millennia of technological development to overcome, if it can be overcome at all, with the physics we understand. We're in a peculiar moment in human history. Our understanding of the cosmos has exploded over the past few decades. We know more about the universe now than at any previous point in our existence. We've discovered thousands of exoplanets. We've observed the cosmic microwave background radiation, the afterglow of the Big Bang itself. We've detected gravitational waves from colliding black holes billions of light years away. We've peered back in time to see galaxies forming when the universe was young. Yet for all this knowledge, for all our technological sophistication, we remain confined to one tiny planet, orbiting one unremarkable star. We've sent 12 humans to walk on the Moon, a journey of less than 400,000 kilometers. We've sent robotic probes throughout our solar system, with Voyager 1 now over 23 billion kilometers from Earth, farther than any human-made object has ever traveled. That sounds impressive until you realize it's still only about 0.2% of a light year. After nearly 50 years of travel, Voyager has covered roughly 1/5000th of the distance to Alpha Centauri. This juxtaposition, vast knowledge paired with severe physical limitations, creates a kind of cosmic claustrophobia. We can see the universe in incredible detail, but we're trapped in our small corner of it, looking out like prisoners peering through windows at a world we cannot access. Some scientists and philosophers argue that this might be a common situation for intelligent life throughout the universe. The so-called Great Filter hypothesis suggests that there are enormous barriers preventing life from developing into spacefaring civilizations capable of colonizing other star systems. Maybe the origin of life itself is incredibly rare. Maybe the evolution of intelligence is a cosmic fluke. Or maybe, and this is the troubling possibility, intelligent species typically reach our level of development, discover the enormous barriers to interstellar travel, and either destroy themselves through war or environmental catastrophe, or simply stagnate, never developing the technologies needed to spread among the stars. If interstellar travel is as difficult for other civilizations as it appears to be for us, then the universe might be filled with isolated pockets of intelligent life, each confined to their home star systems, aware of each other through radio signals or other detectable signatures, but forever unable to meet, trade, share cultures, or exchange knowledge in person. We might be surrounded by civilizations facing exactly the same frustrations we face, staring at nearby stars they can observe but never visit. The Fermi paradox, named after physicist Enrico Fermi, poses a simple but profound question. If the universe is vast and ancient, if there are billions of potentially habitable planets, why haven't we detected any signs of advanced civilizations? Where is everybody? One possible answer is that interstellar travel is simply too difficult. Civilizations arise, develop technology, discover the universe around them, but remain trapped in their home systems, unable to spread or establish the kind of galaxy-spanning empires that science fiction imagined. This possibility is both comforting and deeply lonely. Comforting because it suggests we're not uniquely incompetent or limited, that the challenges we face are universal rather than unique failings of human civilization. Lonely because it implies we might share the universe with countless other intelligent species, yet never communicate meaningfully, never meet, never know each other except as faint signals across impossible distances. Radio communication with other civilizations, assuming any exist within range, faces its own distance-related challenges. Radio signals travel at light speed, meaning even a conversation with Alpha Centauri would involve 8.5 years between sending a message and receiving a response. A dialogue would span decades or centuries. You couldn't have a conversation in any meaningful sense. You could exchange information, share knowledge, perhaps even develop relationships over multiple generations, but the immediacy of real communication would be impossible. With civilizations farther away, the delays become absurd. A star system 100 light-years distant would require 200 years for a simple back-and-forth exchange. Civilizations rise and fall in less time. By the time you received a response to your message, the civilization that sent it might have gone extinct, transformed into something unrecognizable, or simply lost interest in communicating with distant strangers. These considerations have led some researchers to focus on METI, messaging to extraterrestrial intelligence, rather than SETI, the search for extraterrestrial intelligence. Instead of passively listening for signals, METI advocates actively transmitting messages to nearby star systems, including Alpha Centauri. The idea is to establish a kind of cosmic internet, where civilizations separated by vast distances exchange information asynchronously, like emails with decades-long delays, building up archives of knowledge and culture that persist across generations. Critics worry about the risks of announcing our presence to potentially hostile civilizations, though the truth is that our radio and television broadcasts have been leaking into space for over a century. Any sufficiently advanced civilization within 100 light-years has probably already detected our presence if they're looking. The idea that we could somehow hide at this point seems naive. The philosophical implications of these vast distances extend beyond mere practical concerns about travel and communication. They fundamentally challenge our place in the universe and force us to confront questions about meaning, purpose, and the nature of existence itself. For most of human history, we've operated under the assumption that we could eventually reach anywhere we could see. Ancient humans saw mountains on the horizon and learned to climb them. They saw distant lands across water and built boats to reach them. Even the moon, hanging in the sky for countless generations as an unreachable symbol of the impossible, eventually felt human footsteps. We've developed a deeply ingrained cultural narrative that distance is merely a temporary obstacle, that with enough time, ingenuity, and determination, humans can go anywhere. The distances between stars challenge this narrative at its core. These aren't merely difficult journeys that require better technology or more resources. They represent barriers that might remain impassable regardless of our technological development, limitations imposed by the fundamental structure of space-time itself. Learning to accept that some destinations might genuinely be unreachable, that some questions might remain forever unanswered, that some mysteries might persist despite our best efforts, requires a profound shift in how we think about humanity's relationship with the cosmos. This acceptance doesn't mean giving up or abandoning curiosity. Rather, it means developing a more mature relationship with the universe, recognizing both our capabilities and our limitations. We can study distant stars and planets through telescopes. We can send robotic probes, even if they take decades or centuries to arrive. We can build increasingly sophisticated instruments that reveal the universe's secrets without requiring us to physically travel to every interesting location. In many ways, this mirrors how we study other aspects of reality. We can't visit the interior of the sun, but we understand it through mathematics, spectroscopy, and theoretical physics. We can't travel back in time to witness Earth's formation, but we understand it through geology, chemistry, and careful observation. We can't see individual atoms with our eyes, but we've developed instruments and theories that reveal atomic structure in exquisite detail. Direct physical presence isn't always necessary for genuine understanding. Perhaps interstellar distances are teaching us a similar lesson on a cosmic scale. Understanding doesn't require presence. We can know about Alpha Centauri, study its planets, learn about their atmospheres and compositions, and develop genuine scientific knowledge without ever sending humans there. This knowledge might be incomplete in certain ways, lacking the richness of direct experience, but it's still valuable, still meaningful, still represents genuine understanding of reality. Yet something in the human spirit rebels against this acceptance. We don't just want to know about other worlds intellectually. We want to experience them viscerally, to breathe alien air, to feel alien rain, to walk under alien skies. The knowledge that such experiences might be impossible, that we might be forever confined to observing rather than participating, creates a profound sense of cosmic longing, a nostalgia for places we've never been and might never visit. This longing drives much of our continued interest in interstellar travel, despite the enormous obstacles. Projects like Breakthrough Starshot aren't purely rational exercises in scientific investigation. They're expressions of that deep human need to reach beyond our grasp, to attempt the impossible, to refuse to accept limitations even when those limitations appear fundamental. There's something almost defiant about launching tiny spacecraft toward another star system, knowing the journey will take decades and the chances of success are uncertain. It's a statement that we refuse to be imprisoned by distance, that we'll find ways to reach out even if we can't physically go ourselves. The development of increasingly sophisticated artificial intelligence adds another dimension to this discussion. If we can create machine intelligence that equals or exceeds human cognitive capabilities, does it matter whether humans personally visit other star systems? Could we send AI representatives to explore on our behalf, experiencing alien worlds through their sensors, making discoveries and sending back information? This raises deep philosophical questions about consciousness, experience, and what exploration really means. Would an AI visiting Alpha Centauri really represent humanity exploring that star system? Or would it just be a very sophisticated robot following programming? Does experience require consciousness as we understand it? Can machines genuinely explore, or do they merely collect data according to their design parameters? These questions don't have clear answers. Our understanding of consciousness remains frustratingly limited despite centuries of philosophical inquiry and recent advances in neuroscience. We don't fully understand what makes human consciousness different from sophisticated information processing. We can't say with certainty whether future AI systems might develop genuine subjective experiences or whether they'll remain philosophical zombies, processing information without any inner life. If we could develop AI that genuinely experiences the universe in ways comparable to human consciousness, the ethical implications become complex. Would we have obligations to these intelligences? Would sending them on one-way missions to other stars constitute a kind of exile or imprisonment? Or would they perhaps be better suited to interstellar travel than biological humans, unconcerned with the passage of time, unburdened by the need for life support, potentially capable of existing for centuries or millennia? Some futurists propose that humanity's future might involve transitioning away from biological existence entirely, uploading consciousness into digital substrates that could more easily survive the rigors of interstellar travel. A human mind running on advanced computers wouldn't need air, water, or food. It could be backed up and duplicated. It could potentially experience time differently, running faster or slower than biological consciousness. It could survive radiation that would kill biological tissue. These concepts remain purely speculative, probably impossible with current technology, and raise profound questions about identity and continuity of consciousness. If you upload your mind into a computer, is it still you, or is it a copy while the original you dies? Can consciousness transfer from biological to digital substrates, or would the process create a new entity that merely believes it's you while the original consciousness ends? Philosophy has grappled with similar questions about personal identity for centuries without reaching definitive conclusions. Setting aside these speculative possibilities, we're left confronting the reality of our current situation. We exist as biological organisms adapted to one specific planet. We've developed technology that allows us to briefly venture into nearby space, but we remain fundamentally creatures of Earth. The distances to other stars represent barriers that our current biology and technology cannot overcome. This situation might persist for decades, centuries, or potentially forever. We might develop breakthrough technologies that enable practical interstellar travel. We might transition to post-biological existence better suited to cosmic exploration. We might discover physics beyond our current understanding that permits faster-than-light travel or other methods of crossing vast distances. Or we might remain confined to our solar system indefinitely, exploring the universe through telescopes and robotic proxies, never experiencing other worlds firsthand. Each of these possibilities profoundly affects humanity's long-term future. If we remain confined to Earth or our solar system, we face ultimate extinction when our sun eventually dies, roughly 5 billion years from now. That seems impossibly distant, but on cosmic timescales it's a mere blink. Everything we've ever accomplished, every thought, every creation, every life that ever existed on Earth would ultimately be erased when our star expands into a red giant and consumes the inner planets. Spreading to other star systems offers a path to genuine long-term survival, A multi-system civilization could potentially persist for trillions of years, outliving individual stars, adapting to changing cosmic conditions, potentially even surviving until the heat death of the universe in the incomprehensibly distant future. But accessing that potential requires overcoming the barriers that currently confine us to one star system. The distance to Alpha Centauri thus represents more than just a measurement. It's a test of whether intelligent life can transcend its origins, whether consciousness and technology can overcome the fundamental limitations imposed by cosmic distances, whether minds that evolved in one tiny corner of the universe can genuinely become citizens of the cosmos or remain forever trapped near their birthplace. We don't know the answer yet. We're still in the earliest stages of this test, barely capable of leaving our planet's surface, taking our first tentative steps into space. The Voyager probes, our farthest-reaching ambassadors, have only just begun their journey through interstellar space after nearly 50 years of travel. They've crossed the boundary where the sun's influence gives way to the interstellar medium, but they won't approach another star for tens of thousands of years, and they'll be silent and dead long before then. Looking toward the future, we can identify several potential pathways that might eventually enable practical interstellar travel, though all require technological advances far beyond our current capabilities. Understanding these pathways helps clarify both the enormity of the challenge and the kinds of developments that could genuinely change the equation. First, there's the incremental approach, steadily improving our propulsion technologies, energy generation, materials, science, and life support systems until interstellar missions become feasible. This represents the conservative, scientifically grounded path that doesn't require any revolutionary breakthroughs in physics, just centuries of sustained engineering progress. We'd develop increasingly efficient fusion reactors, learn to manufacture antimatter in useful quantities, perfect recycling systems that can sustain humans indefinitely in closed environments, and gradually build the infrastructure throughout our solar system needed to construct and launch generation ships. This pathway assumes continued technological progress at rates comparable to what we've experienced over the past century. Given that we went from the first powered flight to landing on the moon in just 66 years, from the first computers filling entire rooms to smartphones in everyone's pockets in roughly the same time frame. It's not unreasonable to imagine that several more centuries of development could yield technologies that make interstellar travel possible, if not easy. The challenge with this pathway is maintaining the necessary focus and investment over such extended timescales. Human societies struggle to coordinate on projects spanning mere decades. Climate change, for instance, represents a threat we've understood for over 50 years, yet meaningful coordinated action remains frustratingly incomplete. How do we maintain commitment to interstellar exploration across centuries when the benefits won't materialize for generations? Perhaps the answer lies in making the journey toward interstellar capability valuable in itself. Developing the technologies needed for generation ships, fusion propulsion, closed-loop life support, and sustainable space habitats would revolutionize life throughout our solar system. These aren't technologies useful only for reaching other stars. They enable permanent settlement of the Moon, Mars, the asteroid belt, and moons of the outer planets. They create opportunities for mining resources, conducting scientific research, and establishing backup populations that protect humanity against extinction from planetary catastrophes. A civilization that has thoroughly settled its home solar system, with millions or billions of people living in space habitats and on various worlds, would naturally develop many of the technologies needed for interstellar travel as byproducts of its ordinary economic and social activities. The jump from a solar system-spanning civilization to attempting interstellar missions becomes much smaller than the jump from our current Earthbound civilization to interstellar capability. This suggests that the realistic timeline for human interstellar travel might look something like this. The next century sees continued expansion of human presence in Earth orbit, establishment of permanent lunar bases, and the first crewed missions to Mars. The following century, roughly 2100 to 2200, sees exponential growth in space-based populations, exploitation of asteroid resources, and the establishment of self-sustaining colonies throughout the inner solar system. By 2200 to 2300, humanity becomes a genuinely multi-planet species with economic and industrial capabilities in space, rivaling or exceeding Earth-based capabilities. Sometime in the 23rd or 24th century, with this foundation in place, the first serious attempts at interstellar missions might launch. These would likely be robotic initially, testing technologies and gathering data about nearby star systems. Later, perhaps in the 25th or 26th century, the first-generation ships might depart, carrying human populations toward Alpha Centauri, Tau Ceti, or other nearby stars with potentially habitable planets. This timeline assumes no major catastrophes, continued technological progress, and sustained commitment to space exploration. Any of these assumptions could fail. Global conflicts, environmental collapse, economic depression, or simply shifting cultural priorities could delay or prevent this progression. Conversely, unexpected breakthroughs could accelerate the timeline dramatically. Which brings us to the second pathway, revolutionary advances in physics that fundamentally change what's possible. Throughout history, paradigm shifts in our understanding of nature have opened possibilities that previously seemed impossible. Newtonian mechanics enabled the prediction of planetary motion and eventually spaceflight. Quantum mechanics revealed a subatomic world that enables modern electronics, computers, and telecommunications. General relativity showed us that space and time are flexible, opening conceptual space for ideas like wormholes and warp drives. We know our current understanding of physics is incomplete. Quantum mechanics and general relativity, our two most successful theories, are mathematically incompatible. They both work brilliantly within their domains, quantum mechanics for the very small and general relativity for the very large, but they can't both be fundamentally correct because they give different answers when applied to situations involving both quantum effects and strong gravity, like the interior of black holes or the first moments after the Big Bang. Physicists have spent decades searching for a theory of quantum gravity that unifies these frameworks. String theory, loop quantum gravity, and various other approaches have been proposed, but none have been experimentally verified. We don't know which, if any, of these theories correctly describe reality, and we don't know what new physics might emerge from a successful theory of quantum gravity. It's possible, though purely speculative, that a complete understanding of quantum gravity might reveal new possibilities for manipulating space-time, generating exotic forms of energy, or accessing higher dimensions that could enable faster-than-light travel or shortcuts through space. We can't count on such discoveries, we can't even be confident they're possible, but history suggests that deeper understanding of nature often reveals unexpected capabilities. Even without exotic physics, better understanding of more conventional but poorly understood phenomena might open new pathways. Dark matter and dark energy together constitute roughly 95% of the universe's mass energy content, yet we barely understand what they are, let alone how to manipulate or harness them. Vacuum energy, the quantum fluctuations of empty space itself, represents an enormous energy density that we currently can't access, but that might be exploitable with sufficient technological advancement. These represent long-shot possibilities, things we can't rely on but can't completely rule out. There are reasons to continue investing in fundamental physics research, not just for practical applications, but because understanding reality more completely might occasionally reveal game-changing capabilities. The third pathway involves a fundamental transformation of what humans are. This represents the most speculative but potentially most transformative possibility. If we develop technologies that allow us to enhance human biology, merge with machines, upload consciousness to digital substrates, or otherwise transcend our current biological limitations, the constraints of interstellar travel might change dramatically. Imagine humans who don't age, whose bodies can be repaired indefinitely, who can enter suspended animation for centuries without degradation. Generation ships become unnecessary because the original crew can survive the entire journey. Or imagine consciousness existing as information patterns that can be transmitted at light speed, beamed to other star systems, and instantiated in new bodies constructed at the destination. The journey time becomes irrelevant because you essentially teleport your mind, though this raises profound questions about whether the receiving end is really you or merely a copy. These possibilities edge into transhumanism and posthumanism, philosophical and technological movements that envision humanity evolving beyond its current form. Critics worry about losing essential aspects of human nature, about creating technologies that might destroy what makes us human in the first place. Advocates argue that humans have always been technological beings, that we've already transcended our evolutionary origins through culture, language, and tools, that further enhancement represents continuation rather than abandonment of humanity's trajectory. These debates will intensify as technologies like genetic engineering, neural interfaces, artificial intelligence, and life extension continue developing. We're already seeing the early stages of human enhancement through medical technologies, prosthetics, and pharmaceutical interventions. The question isn't whether humans will change, we're changing constantly, but how much change is desirable and how we navigate the ethical complexities of deliberately reshaping ourselves. For interstellar travel purposes, the key insight is that the difficulties we face assume humans remain fundamentally similar to how we are now. Change that assumption, allow for radical transformation of human nature, and the calculation changes. Whether such transformations are desirable, ethical, or even possible remains deeply uncertain, but they represent potential pathways worth considering. Ultimately, the distance to Alpha Centauri serves as both a challenge and an inspiration. It's a measure of how far we have to go, how primitive our current capabilities remain, how vast and indifferent the universe is to our ambitions and desires. 4.3 light-years sounds small when you say it quickly, but it represents a barrier that might take centuries or millennia to overcome, if we overcome it at all. Yet knowing the distance, understanding the challenge, measuring the gap between where we are and where we want to be, represents progress in itself. Ancient humans looked at the moon and saw a mysterious light in the sky, a god or spirit or unreachable symbol. We looked at it, measured the distance, calculated what it would take to get there, and went. The journey from mystery to destination took thousands of years of gradual understanding, then a few decades of focused effort once the knowledge and technology aligned. Alpha Centauri represents our current moon, a destination we can see and measure but not yet reach, a challenge that seems impossible until suddenly it isn't. Whether we'll eventually make that journey, whether humans or our descendants or our AI successors will stand on planets orbiting those distant suns, remains genuinely unknown. The universe isn't obligated to make our dreams achievable. The laws of physics don't care about our ambitions. But we keep looking up, keep measuring, keep planning, keep pushing against the barriers that confine us. That's what we do, that's what makes us human. And maybe, eventually, that stubborn refusal to accept limits will carry us to the stars, or at least teach us profound truths about ourselves and our place in the cosmos in the attempt. If you're fascinated by what happens when we push the boundaries of speed and approach that ultimate cosmic limit, check out the video on the screen. What actually happens if we reach light speed? We dive deeper into the bizarre reality of time dilation, length contraction, and what the universe looks like when you're traveling at 99.9% the speed of light. See you there.